If you've watched our other videos on derivatives, you should have a fair understanding of how to find derivatives of functions. To review, these functions are usually written as f of x, and you'll find the derivative of f, or f prime of x. Equivalently, the function may be called y, and you'll find y prime, where f of x, or y, is written in terms of x. Sometimes, though, you may need to take the derivative of a function that is not in this format. For example, the equation 2xy minus y squared equals 5x features multiple terms with y, and it cannot simply be rearranged to give y as a function of x. For these, we have to use a process called implicit differentiation to find the derivative of y with respect to x, or dy dx. Today, we'll be building on some of the concepts we've covered in other videos, including the chain rule and the product rule. Let's start by considering the relation 6xy minus x squared equals 3y and finding dy dx through the process of implicit differentiation. To do this, we'll want to take the derivative of each term in the relation. We can start by writing d dx in front of every single term. Remember, d dx is just a notation for saying take the derivative with respect to x. When we do this, we get d dx 6xy minus d dx x squared equals d dx 3y. The second step in implicit differentiation is taking each of these derivatives. Let's take a look at these terms one at a time. First, we have the derivative of 6xy with respect to x, but how can we take the derivative with respect to x if there's a y in the term? To do this, let's remember that when we talk about y, we typically are talking about y itself being a function of x. With implicit differentiation, the same idea applies. We're going to consider all y's to be implicit functions of x. For this term then, we have 6x times a function of x. As with derivatives of other products, this calls for us to apply the product rule. Remember, the product rule says that for two functions multiplied together, the derivative is the first times the derivative of the second plus the second times the derivative of the first. So the first times the derivative of the second gives us 6x times dy dx because the derivative of y, d dx of y, can be written as dy dx. Continuing with the product rule, we add the second times the derivative of the first, which gives us y times 6. Putting these together, we have 6x times dy dx plus 6y as the derivative of the first term. Next, we have minus d dx of x squared. Since this term doesn't have any y's, we can just take its derivative normally and get minus 2x. Finally, on the right side, we have the derivative d dx of 3y. Remember, since the derivative of y is dy dx, we get 3 times dy dx. Putting all the pieces together, we now have 6x times dy dx plus 6y minus 2x equals 3 times dy dx. Since the goal is finding dy dx, we now just need to isolate dy dx on one side of the equation. Let's move 6x times dy dx to the other side of the equation so we can have all the dy dx's together. To do this, we subtract 6x times dy dx from both sides of the equation. From here, we can factor out the dy dx's. Then divide both sides by 3 minus 6x. And just like that, we have the solution. The three steps of implicit differentiation are writing d dx in front of each term, taking the derivative of each term with respect to x, and then solving for dy dx. Let's try this with another example. Use implicit differentiation to find dy dx for the relation y cubed minus 4x equals xy. Just like in the last example, we can start the implicit differentiation process by writing d dx in front of each term. Next, we need to take the derivative of each term with respect to x. Notice that the first term is y cubed. Unlike y to the first power, we cannot simply take the derivative to be dy dx. Since we are taking the derivative with respect to x, we have to be careful and remember that y is a function of x. With this first term, we are essentially seeing a function, y, inside another function, a cube function. Sound familiar? Because we have a function inside a function, we need to use the chain rule for this term. Remember, the chain rule says that the derivative of a composite function, f of g of x, is equal to the derivative of the outside function with the inside function unchanged times the derivative of the inside function. So in this problem, the derivative of y cubed with respect to x is equal to the derivative of the outer cube function with respect to y, 3y squared, times the derivative of the inner function with respect to x, dy dx. This is a very important step to remember with implicit differentiation, since it comes up quite frequently. In fact, anytime you have to take the derivative of a term involving y to some power other than 1, you'll need to use the chain rule and multiply by dy dx. Let's take the derivatives of the other terms now. The derivative of minus 4x with respect to x is minus 4. On the right side, the derivative of xy with respect to x can be found using the product rule. The first times the derivative of the second gives us x times dy dx, and the second times the derivative of the first is y times 1. So we get x times the derivative of y with respect to x plus y. The final step of implicit differentiation is solving this equation for dy dx. To do this, let's move x times dy dx to the left side and move the minus 4 to the right side. By subtracting x times dy dx from both sides and adding 4 to both sides, we get this. Now let's factor out dy dx from both terms on the left side. Finally, we can get dy dx by itself by dividing both sides by 3y squared minus x. You may have noticed that both of the solutions in this lesson so far have included the letter y in the derivative. This is nothing to be worried about though, and is just a consequence of how implicit differentiation works. Rest assured, as long as you follow the 3 steps properly, and remember to apply the chain rule and the product rule when they're needed, you'll be on the right track. Let's work through one more example. Use implicit differentiation to find dy dx for the relation sine of y squared equals 5x squared plus y. First, we can start by writing d dx in front of each term. The first term is going to be the trickiest. Since we have a function, y squared, inside the sine function, we're going to need to use the chain rule. The derivative of the outside will be cosine, so we are going to have cosine of y squared times the derivative of the inside. But what is the derivative of y squared with respect to x? Since y is not to the first power, we are actually going to need to use the chain rule a second time. Now the outer function is the square, while the inner function is y. So the derivative of y squared with respect to x will be 2y times dy dx. We can now rearrange this a little bit on the left side, and we'll get 2y times cosine of y squared times dy dx as the derivative of the first term. Fortunately, the other 2 derivatives in this problem are much simpler. The derivative of 5x squared is 10x, and the derivative of y can be written as dy dx. The final step is, once again, to solve for dy dx. To do this, let's move dy dx from the right side to the left side by subtracting it from both sides. Then we can factor out dy dx from the terms on the left side. Dividing both sides by 2y times cosine of y squared minus 1, we get the solution. Implicit differentiation can seem like a tricky topic in calculus, but keep in mind the 3 main steps. First, write d dx in front of all terms in the relation. Second, take the derivative of each term, taking special care to remember that y is a function of x and will often require the chain rule for proper execution. Third, solve the resulting equation for dy dx. As always, with a little practice, you should feel more and more confident with implicit differentiation. I hope this video was helpful. Thanks for watching and happy studying.